So this lesson 23 for classification trees. So we're going to talk about basically doing the same thing that we did last time with the regression trees, but we're going to do them with classification trees where we use the qualitative responses instead of a numerical response, so a real number. For example, uh, with regression trees, maybe we're trying to predict the price of a home that's sold, given all these different predictors like the number of bedrooms and so on and so forth, or the number of bathrooms or the square footage of the house. Whereas maybe in a qualitative piece, maybe you're seeing where it's a high, a low, or a medium, or even if the home is going to sell next month, right? So a yes or a no, right? Is the home going to sell next month based on certain factors? I mean, so that's the kind of things that we're going to use classification trees for. So again, the difference between maybe something I do in class, like you're gonna sit here and watch me like write this out in class or on the video, because you can always stop the video and just sort of write out, okay, here's what he was talking about there, or you can rewind it or whatever. But in class, you really don't have that option. So so that's why I write it out in class so that you have a time to stick it in your notes. Okay, so when we grow regression trees, we used residual sum squares or sum of squared errors, which is not available to us in this setting, right? So I can't have an SSE for a qualitative response. And so instead of doing that, what we'll see below are three different techniques in order to get at that. I'm just going to walk through what we're doing, right? So remember the idea. We want to now binary separate the predictor space into two different regions. So in this case, we have region 1 and region 2, and my splitting factor is S is equal to 4. My split is S is equal to 4, so that's the value, the x2 value. And why is it x2? Because J is equal to 2. So I've drawn a line here to differentiate between that. Now, is this the best one? I don't know. It could be, but it's probably not, because you probably have to move this line and figure out what the Gini index is, how we're going to do it. But I'm going to introduce a couple different ways to figure out like kind of how good is this region and how good is that region. So just realize that what we're talking about for the next three things are how good is a particular region. So for example, in the book, they talked about this PMK hat. It says PMK hat right here, right? So you might have saw that. It's just the proportion of the training observations in region M from class K. So in region M, so in other words, M is the row. So if we're going to put this together in a matrix, M would be the row and K would be the column, and M would be like region 2. So we would have M21 and M22, and then region 1 would be 1, 2, or 1, 1, and 1, 2, right? So if I only have two classes, I only have two columns, right? So I have a square matrix in this case. So let's go ahead and actually calculate this, right? So E for A region is 1 minus the max of P MK hat. So, okay, before we do that, let's actually calculate these MK hats, right? So this might be region 1 down here. And so the question is, what is class 1? So what is P11, right? Hat. And I put the hats on here I guess at the end after I discovered that they didn't have the hats on them. And so the question is, well, how many points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why the 10's on the bottom. And the question is, well, how many class 1s are there? So there's there's 7 of those, and then the 3 red ones are right there, right? So you have 7/10 for P11 and 3/10 for P12. And as you can imagine, but if we only have two classes, then this one would be 1 minus that one, and this one would be 1 minus that one, because there's only two classes that it could possibly be in. Okay, so the region 2 up here has one class 1 in it, right? So 2, 1. So region 2 class 1 is 1 over 11, right? Why? Because there's 11 data points in here, and 10 over 11 for P22 hat. All right, now that we have these numbers, it's very simple just to go in and say, all right, tell me the classification error rate is E1 for region 1. So 1 minus max K. Well, what is max K? When K is equal to 1, you come over here and go, it's when K is equal to 1, we have, P hat 1, 1. So max K. Oh, okay. So I see what we're doing here. So we're down here in this region, and the question is, well, which one of these two maximizes the p hat, right? So it's k is equal to 1 or k is equal to 2. And then the red piece here says, well, k equal 1 is actually maximizing that. So 1 minus point, so 0.3 is the E1. And then you do the same thing. You say, all right, max, the maximum for this one would be 1 minus, so for region 2, we're going to go in here and we're going to see that that would be the max. So 1 minus 10 over 11 would be 0.09 or 1 over 11. And then we just add those two errors together and we get 0.39. So we're going to find out later on that there's a different sort of, actually the next lesson, lesson 24, there's a different way to kind of put these together in order to have the overall error rate. But we'll see that in actually lesson 24. So so the Gini index of M, so how would we put that together? That would be this G of 1 to K of all this. So again, let's go back and remember. So if we're talking about region M equals 1, so we're talking about this one, well then we would get 7/10 and 3/10, right? So it's 7/10 would be here, 1 minus 7/10 would be 3/10. And then again, it's a summation sign, then you go to the next one and you get 3/10 and 7/10, and that would be 0.422. Or I'm sorry, 0.42. So this would be, there would be 0.42 Gini. And this side would be 0.0165 Gini. And that would be calculated the same way. PMK hat would be, let's see, so PMK hat would be, so for K is equal to 1, so M is equal to 2, K is equal to 1, so 2, 1 would be 1/11, and that's where you're getting the 1/11 from. And then 1 minus 1/11 is 10/11, and then 2, 2 would be 10/11, and then 1/11, and we get 0.65. This is not how we're going to do this. We're not going to add those two together. There's a different way of putting these together if we're talking about what the Gini is for this split. And again, we'll talk about that in lesson 24. It's just a measure. So this is a measure of variance. And so I'm going to go ahead and put a circle around the entire sort of explanation that this is actually a variance. So this is using the Bernoulli random variable and understanding that the variance of a Bernoulli random variable, if you just did all the math that's sort of associated with that, you'll get P times 1 minus P, where P is the probability that X is true. In this case, what we're talking about is the probability that you're actually in one of the classes. So either in the class or you're not in the class. With probability P and probability 1 minus P, and so and what we're saying is this is the estimate for that Bernoulli random variable in that particular region, and it's all based on the number or the proportion of training points that are in that region that we broke it up into. Okay, an observation is a member of a certain class within a region with Bernoulli this PMK hat. So that's the estimation for that. All right, and the last one is just, and it kind of, I mean, let me make sure I get this on the same, it's sort of related to this one, right? So what's happening here is it's negative, and why is it negative? Because this is going to be a negative number, because this PMK hat is going to be some number between 0 and 1, because it's a proportion of folks in each class. And this, as we get closer to 1, goes to 0. So as PMK hat gets closer to 1, it goes to 0. And obviously, as this one goes to 0, it gets closer to 0. So this kind of looks like this one, because it's the same thing here. As this gets closer to 1, this goes to 0. So these functions are sort of the same. They're close, but not exactly, because entropy is a little different. It has a different sort of slope on there. And so I just show you how to calculate it. So PMK hat for region 1 is 7/10, and that's natural log of 7/10. And it's a negative sign because this thing inside of here would be a negative, and then negative 3/10, natural log of 3/10, and you can see PM2 is equal to that. So you could get your calculator and calculate these suckers out, but I'm not going to do that. I mean, it's very straightforward. Okay, so now what I want to do is take these ideas and then go over to our lesson 23. So this is our lesson 23 classification trees. I'm going to show you some things that were in the van der Plas book. So let's shift enter. Shift enter. Okay, so we have what some of the functions look like, and then I'm going to make some blobs. Where is that coming from? This make blobs thing is in the sklearn data set, so I'm going to use some blobs. And what does that do for us? It allows us to sort of classify this thing. So now I got 4 classification. I got 4 classes that I'm trying to classify this thing as. And this next thing is what comes from the van der Plas book, is just hey, I want to see actually how the thing gets broken up. So if I choose to do, oh, this first one just does a bunch of them, right? So this first one, let's just, I certainly overfit the data. So you can see where I put a box around that one, I put a box. So you just kind of keep going until the Gini index, and I think that's the default. The Gini index is the one that we're using, the objective function, if you will. That's what we're trying to minimize, and you just keep doing that until it doesn't minimize anymore, and that super overfits the data. So we're gonna later on we're gonna look and see how to prevent that from happening. But for right now, we just let it kind of go until it's done. And you can kind of see it puts boxes around everything. Okay, let's use this function that we created up here and see how it does it. So this is one class, and if any other observation were to be in that color, then we would classify it as this class. If any other observation is in this yellow here, we would classify it whatever class the yellow is. And then you got this light blue, and maybe this is purple. Maybe we want to call that purple, and this one sort of blue. In order to, I just want to see kind of what happens from going from 2 to maybe 4, right? So that's what this shows, and I'm doing max leaf nodes. So this is the first break, right? So that's the first split, and then the second split is there, and then the third split is that one right there, right? So now we kind of have, I feel anyway, an idea of you know, if you're over here in this general region, you're going to be yellow. If you're in this general region, you're going to be this purple color. If you're down in here, I mean, I feel like that's the best sort of way to do it, because I have 4 classes. If I separate them in 4 big spaces, then maybe we can we won't overfit the model. And let's take this last one here and let's visualize what the actual model is doing. So shift enter, you can see the same thing. And then let me show what that model looks like. So if x2 is less than 6.261, which is, I'm sure it's that number right there. Here, let me go back up. 6.261, yeah, so it's that number right there that's spatially separating the red. We're going to, you know, separate the data into that. So we got the stuff that's above and the stuff that's below, and then this next one is separating us at x1 is less than -4 points. So that must be -4.22 or 0.422. So that is -0.422, and it only goes up to that point right there. Let's see. So it goes up and separates the data on this side, and these two are on that side, and in this one, and then finally we're going to separate it in between. That looks like x2 again. So x2 is less than 2.567, and then you get these guys and these guys. And then what you want to just go do, it colors them, right? So this one is is what's called a leaf. Because it's the end, that's another leaf, and that's another leaf, and that's another leaf. So you got 4 sort of places here that this happening, or this happened. So we expect this one to have all 68 be in class 3, and you can see all 68. If you look above that number, all of them are coming from that last class. And then you could see maybe what's happening here and so on and so forth. So you can kind of see how this thing's getting divvied up as we walk through it. And this is just another one to show you what max depth does. So max depth shows probably this one, right? So it looks like it just goes down twice, right? So it goes down once and twice. Yeah. And then you can see what that model looks like once and twice. Yep. Okay. So let's look at some real data. So let's look at that heart data. Not sure if you guys went and saw it from the book, but the book describes what each one of these columns represent, and then like chest pain. This part that I want to show you is that you can actually use qualitative variables as well. And so let's look at those. If I hit shift enter on this, you can see the qualitative variable called chest pain. You got these different classes called asymptomatic, non-angenial, if I'm pronouncing that correctly, non-typical, and typical. And so you can see if I want to now classify someone who has asymptomatic chest pain, I'm probably going to say that they do have heart disease. And I'm probably going to say someone angenial, it does not. And then I say that maybe, I guess that's pretty close. Maybe we say that these guys are at a 0 and this one's really close. I probably wouldn't, again, you're going to have to look at how the model sort of uses the Gini index, and then you'd have to use it and compare it to the other variables and see if there's a better split. But you can kind of see why you would want to be able to use these qualitative variables. And let's just see the picture. So all this is a picture of what we got written right here for the table. And you can see that most of the red is over here in 1. And I think that's what we said for that, and so on and so forth. So it's just a different way of looking at it. There's other ways to look at it. This is just how I'm showing you how to do it. All right, so what are we doing now is picking the columns that we want for our X values, and then getting the dummies, and then picking what my response variable is. This AHD means heart disease. I'm not sure what the A stands for. I forget. But I think in the book it just had HD as being a heart disease. But up here you'll see AHD for that thing. So shift enter. And for this particular draw, I got a, again, check out what we're doing here. So I'm modeling it. I'm using Gini. I'm max depth is equal to 3. I'm fitting it to the model with the train, and I'm using the test in order to predict the H's, and I'm showing you the score. So we got 68% correct. And then the C matrix, you can see that on the diagonal are the ones that are good, and the off diagonals are the ones that are no good. But we could hit this again, shift enter. So you see, if I did it with a different set of data for my train and my test, I get 84%. And if I did a different set of data, I get 0.78. So what am I going to do, or what I'm going to do is I'm going to do each of these models like 30 times, and then find an average and find a standard deviation and just map all that stuff out. And I want to use this max depth level. I'm going to go from 2 to 7, right? So for here, I think I did it at just 3, and you could see with just 3, you get a different number depending on which data that you pull out. So here I'm going to let it be random, so I'm not using the same data every single time. So I'm going to have a different number, and I'm going to shift enter, and it takes a second, and it comes back and it says, all right, well, if you choose max depth of 2 for those 30, well, that was the average that you got, and that was the standard deviation. And if you chose 3 as your max level, the average that you got was this. And I feel more comfortable about this number than I do about this number, because I've done 30 of them. I've got some average, I got some standard deviation, I kind of know what's going on, and that's how you want to approach these things. Is you want to say, okay, what are my hyperparameters? And this is called a hyperparameter, this max depth. And you could have chose a max leaf node as well. And so I think in class I was going to ask them to do the same thing with max leaf nodes, but I don't think we got to it in either one of the classes because we got kicked out because of the drill that we were doing. All right, so let's so C rate. So this is just putting into a data frame, and then I'm going to use that data frame to graph. The first one that I didn't like very much because it started 0 and came up, and then it kind of gave you a little error bar. And so I was like, let's use error bar instead. And so if you see that, I like this one a lot better, and you can see which one. Obviously 3 looks like it's better than the rest of them. And again, you could do even more if you wanted to. All right. And then I was going to ask you guys to do figure out what the hyperparameter for max leaf node is. So shift enter. You can see there's more of those. I went down to 16, and C rate, shift enter. Oh, it didn't even stop at 16. Oh, I'm sorry, it did. So 15 is so it didn't go to 16, went to 15. I forgot. I just got Pythoned a little bit. So so then let's look at the error bar. And you can see usually 7 tops out, and sometimes 7's not as good as some of these poor ones, but for the most part, you can see the error bars are about the same. All right, the last thing I wanted to gently introduce today was this idea of this randomized search CV. Now, what this does is it does look for the hyperparameters. You got to put in, so in here you'll see I used 500 iterations, so 500 different things, but it only does it once. So what it's going to do is it's going to use this thing called alpha, CCP alpha. This is sort of like ridge regression that we talked about before, where you're sort of you're penalizing it for having more leaves. So if we were to run this, shift enter, and it's doing a whole bunch of them, it's only going to return the best parameter that comes out of all of them, right? So you see a whole bunch of different things that we put in. I'm going to find out what the best one was, and you can see max leaf node was 5, criteria was Gini, CCP alpha was equal to that, and 7.7657. Now that was only one time doing it. So now what I do is I'm going to take this number, I'm going to pull it down here. So I'm going to create this thing, and I'm going to do it a whole bunch of times. And then what was it, 5? So that would be 5 there. And Gini goes here for our criterion. They only let you use Gini and Entropy. And we go Shift Enter, and we see that 7.4. So it's lower than that number. Ugh. So of course, we need to do a whole bunch of them. Control C, and then Control V. And let's do a whole bunch of them and see what happens. And you can see set 0.74. Now again, that is actually lower than the one that we did up here. I mean, I was getting all of these seemed like they were better than the one that we just did. So randomized search CV might not be as good as they might think because it is random, kind of how you choose the data. I would personally sort of go through each one of the parameters one at a time like this, unless it's very, very long in order to do that. In other words, if each one of these took a very long time to do 30 of them, then maybe I would do the randomized search CV, but I would certainly not do 500 then. We would do something less than that. Okay, well, that's all I got for this lesson. Hopefully this didn't do like it didn't mess up this time and we actually have the stuff. Okay, I'll talk to you guys next class. I hope you got something out of it.